So we have finally arrived at the last chapter in our calculus textbook, chapter 15. So back in chapter 12, we studied vector valued functions, and we used them to model things, things dealing with like curves and things dealing with motion, etc. We want to study two more vector valued functions. We wish to study vector value functions that assign vectors to a point in a plane, as well as assign vectors to a point in space. Now, these types of vector valued functions are referred to as vector fields. So that is the topic of 15.1, is the study of vector fields. Let's start with just some examples. We'll come back to this definition of a vector field in just a second. Let's just start with some examples. So, for example, let's look at some type of rotating wheel. Right? So here's your wheel. Here's your axle. Let's assume that the wheel is rotating on the axle. And my question to you is, what would you predict? What would you predict would happen in terms of velocity as you move away from that axle? Right? So, in other words, the velocity of the spinning here, etc. So as you start to move away from the axle, what would you predict would happen in terms of its velocity? Well, the velocity should increase as you move away from the axle. Now, if we wanted to model this, imagine that there's a function out there, right? And the job of this function is to assign vectors at different points on this wheel. So we might have a scenario where if you plug in the following xy point, it gives you the following vector. If you plug in this point, you get the following vector, and if you plug in this point, you get the following vector. Now, what's interesting is just notice what it is that we can, what information we can obtain from this vector field. For example, we can clearly see the difference in the velocities closer to the axle versus further away. We can also see the direction the wheel is turning just by the just simply by the direction of the vectors. So now imagine, well, actually we'll go to another example. So the next example, this is by the way, this is a type of vector. This is a vector field. The next one is another type of vector field dealing with gravitation. So what we have is let's just assume that we have two objects with mass at these locations. And notice all the vectors that are being plotted. And the question, again, it stands, what information can we obtain from the vector field? Well, one thing that you can notice is that the magnitude of the vectors are the same as long as, when you're equally far apart from the two masses, right? In other words, when m sub 1 is equidistant to m sub 2. So for example, notice that each of these vectors have the same magnitude when you are equally distant. The two objects are equally distant. We can also tell the direction, right? All of your vectors are pointing towards mass sub 2. The force of attraction exerted on m sub 1 by m sub 2 is what's being modeled here. So, okay. This is another type of vector field, what we call a gravitational force field. This is an example of an airflow vector field. But nevertheless, what is it that is required of us? What is it that we want, we have to be able to do? Well, for now, let's start with just a definition of a vector field. So a vector field, we'll start with a plane, right? So mostly what we're going to be doing right now is over a plane, but we could also extend this definition to space as well. But the idea is that a vector field over a plane, region R, first, it's a function. So that's the important thing. So it's a vector valued function. And this function assigns a vector to each point in the region. So this notation here is the notation for the vector valued function. And its job is to assign vectors to various points in whatever region you're dealing with. Now, this is one of the very few times in my calculus courses where I will ask you to sketch by hand these vector fields. So let's start with the following. So the following vector field is defined as negative y in the I direction and plus x in the j direction. And what I'm going to do is I'm going to try to give you some steps here, but again, let's start with the understanding that f of xy, this is the function, and it is a function that assigns vectors to points. So in other words, this is itself a vector, right? That makes sense. If I plug xy into this function, what comes back out is a vector. Now, the way I like to do this is I like to arbitrarily choose some distance c from the origin, right? And in that case, what we're going to do is we're going to let that c be the magnitude of the vector. Now, obviously, you could choose all different types of, you could sketch all different types of vectors, but if you listen to me, I can save you a little bit of time because what we're going to do is we're going to start off with choosing some easy values of c, distances to work with. Just remember that, just recall that, I should say, that the magnitude of a vector is fairly simple. It's just the square root of each component squared. So let's go ahead and get started. So in this case, I'm going to be plugging in the I component and the j component, right? J component. And then I'm going to be squaring them, and then I'm going to be setting that equal to c. So in this case, that would be the square root of x, I'll go ahead and write it as y squared first. The square root of y squared plus x squared is equal to c. In other words, y squared plus x squared is equal to c squared. Well, this is just a circle. So when I choose a value for c, I'm really choosing the radius of this circle, right? So again, let's make it as easy as we can. We'll start off, we'll let c equal 1, right? So that gives me y squared plus x squared is equal to 1 squared. Now, so with a circle of radius 1, obviously there's an infinite amount of points that we could plot our vectors at, but let's just choose some easy points to work with, right? So we're going to choose 0, 1, 0, negative 1, 1, 0, negative 1, 0, right? So these are what we're going to get 4 points. If you don't mind, give me four points, 4 vectors of distance 1. So let me go ahead and plot them. So we got the following points. And we want the vectors that would be plotted at each of these. So the points that we are interested in, these are the points 1, 0, and then we got 0, 1, and then we have negative 1, 0, and then 0, negative 1. All right. And now what we're going to do is we're going to take this point, we're going to plug it into our vector function, and what's going to come back out is the vector that we're going to plot. Okay? So we're going to be plugging 1 in for x. We're going to be plugging 0 in for y. So what is that vector? Well, that vector f of 1, 0. Well, you give me that the I is going to cancel out, and we're just left with 1j, or just j. All right, so this is what I'm going to expect you to plot. And please understand that you need to give the magnitude as well as the direction. So the magnitude is 1, and the direction is in the j direction. So let me go ahead and do that. I'll take my time with the first few. So I'm plotting a vector right here at 1, 0. Now from here it's going to be moving in the j direction, so that's this way, and it needs to have a length of 1. Okay? Now I'm going to go ahead and do the same thing with the other 3 points. So now it's 0, 1. So that's going to be 0 for x, 1 and for y, so that's going to be negative I. I'm going to go ahead and do all this first. Negative 1, 0, that's going to be negative j. 0, negative 1, so that's negative 1, so that's just going to be I. So, all right, so let's go to the point 0, 1. And let's go ahead and plot. We're going to be moving in the negative I direction, a length of 1. Okay, and you can kind of start to fill in the details from here. So from negative 1, 0, we're moving in the negative j direction, a length of 1. And finally, from the 0, negative 1, we're moving in the I direction, a length of 1. So when I grade these, I'm grading that you got the directions correct as well as the magnitudes correct. All right. And so this is good. This is starting to tell me that this object is rotating. You would want to go a little bit farther when you're plotting. Try to get me at least 8 vectors. So we have 4 of them right now. So you might do the same thing, only you would want them at a different distance. So now you might have, if we let c equal 3, then we have x squared plus y squared is equal to 9. So now that we have a radius of 3 basically for our circle, the 4 points that we're going to be plotting is 3, 0, 0, 3, negative 3, 0, 0, negative 3. And the game is the same. You're going to be plugging each of these into your vector function, and what comes back out is the vector that you're going to plot. So that's going to be 3j, negative 3i, negative 3j, 3i. All right, so I'm just going to plot each. I'm going out to a distance of 3, and I'm going to go ahead and just make sure I get both the direction and the magnitude correct. So there is 3 moving in the j direction, and then that's at 0, 3 moving in the negative I direction. And you can kind of fill in the details here, right? So you get the gist. So what are you doing? Well, if I ask you to sketch a vector field, try to give me 8 vectors. And then just make sure your vectors are both pointing in the right direction and representing the correct magnitude. Okay? All right. So we're gonna be moving on to conservative vector fields, but really quickly, I'll just ask you, just a quick question. So assume that you have water, flowing through some type of water hose, and you wanted to sketch the velocity of the water pressure through that hose, right? So in other words, you would have vectors in this region that would represent the velocity of coming out of that water hose. Now I'm just just making up some type of arbitrary function here, but the real question is, if you were to look at that vector field from that hose, what would you expect? Where would you assume the velocity is the greatest? Well, it should be right at the center, right? And then the velocities at different positions coming out of that water hose would be a different magnitude, but in the center you would expect to find the greatest velocity. Okay. So what am I talking about? Conservative vector field. So no, your vectors are not politically affiliated. So the conservative has nothing to do with political affiliation. This is just the terminology for a certain type of vector field. Now, what is? Let me read, and then I'll try to give you in other words. So the definition of a conservative vector field. Well, first off, it's a vector field. All right, let me read it. A vector field is called conservative when there exists a differentiable function f such that the vector field is equal to the gradient of f. Now, in other words, so this function f, this is the potential function. And basically what we're saying is, in order to call it the vector field, in order to make the statement that it is a conservative vector field, first, the derivative has to be the gradient, and the gradient of the vector field, the gradient is the vector field, or it is equal to the vector field. So the gradient of f is equal to this vector field. Okay, let me see. I think we probably should be coming up on a break. Let me do this. I'll do this little before I get into tests and stuff like that in the next video. But take the following vector field: 2xi plus yj, and the question is it conservative? Okay, so how do I take this information up here to be able to make the statement whether it is or it is not conservative? Well, first off, if it is, there must be some potential function out there, right? There is some f out there such that the gradient of f is equal to this vector field. Now, I'm going to show you how. Well, first off, when we get back from the break, I'm going to show you how to test for if it is a conservative vector field. But then I want to show you how do we go about finding this potential function. So let me just give you some potential function. So I now could, so here is some function that's out there. It'll be our job to find it. But now that we've found it, does the gradient of this function equal our vector field? Well, first off, let's go ahead and find the gradient. So the gradient of f, right? So remember, that's just going to be the partial with respect to x in the I direction plus the partial with respect to y in the j direction. So let's start with the partial with respect to x. So the partial with respect to x would just be 2x. And now let's do the partial with respect to y, which would just be y. So here's your gradient. And you can see that your gradient does match the vector field. So there was a function out there whose gradient was equal to the vector field. So therefore, we can make the statement that yes, this is a conservative vector field. But I'll give you a much cleaner way of going about this in the next videos.